We are discussing about GATE 2007 ECE paper, and this question is related to electronics. Look at the circuit diagram. For the BJT circuit shown, assume that beta of the transistor is very large and VBE is 0.7 volts. Then the mode of operation of BJT is. So what was given is beta of the transistor is very large. Whenever beta of the transistor is very large, that implies nothing but you can neglect the base current. Base current can be generally calculated by using IC by beta. Whenever IC by very large, at that time it is approximately equal to 0. So you can neglect the base current is going to be 0. Okay, and the mode of operation we are interested in. For example, first of all we will see what are the different types of modes of operations are possible with BJT. Okay, so this is the BJT circuit and it will be treated as this is base terminal and it is collector, this is emitter terminal. Okay, so assume that when the current flowing through base is nothing but IB and current flowing through collector is nothing but IC. For example, if you are applying the voltage across base such that the BJT is in the off condition, whenever the BJT is in the off condition, at that time this is base current. Assume that when this is 0. Okay, IB is 0. Whenever the base current is 0, for example, the BJT will be in the off condition, so that it acts as open circuit, there is no collector current flows. So IB is equal to 0 is nothing but that makes IC to become 0. And whenever it is happening, at that time VCE, voltage across VCE, is going to be approximately equal to VCC. So since there is no current is flowing through the output loop, at that time there is no voltage drop across 10 kilo ohm and 1 kilo ohm. By that time the total applied voltage of 10 volts has to be bear by the transistor itself, since it is acting as open circuit under cutoff condition. So this line is going to be treated as cutoff region. During cutoff region, the base current is 0, collector current is 0, entire voltage applied is going to be taken by the collector to emitter only. Okay, now let us assume you are applying the current, you are applying a voltage such that the transistor comes into on condition. Whenever transistor comes into on condition, at that time IB starts flowing. So whenever IB starts flowing, the IC is also gets flowing, so that it will be increases. IC is equal to beta times of IB. So IC and IB are going to be related. So as IB increases, IC is going to be increases. Whenever IC is going to be increases, at that time voltage across VCE is going to be gets reduces is nothing but now out of this 10 volts some voltage is going to be dropping across resistors, so the remaining voltage is only present between collector and emitter, so that the voltage across VCE is going to be gets reduced. And this, the relation between IC and IB, that is nothing but as IB increases, IC increases, it no more continues, and this IC will become saturated at one point, so that this point is going to be treated as IC saturation. So the collector current increases with respect to IB and at one point it becomes saturated. So the value what it requires, the base current, how much of base current it requires to get this IC saturation is going to be treated as IB minimum. So till this point there is a relation between base current and collector current. That relation can be written as IB minimum can be calculated as IC saturation divided by beta. So if you increase IB value by that time, okay, so at this point, saturation point, the voltage VCE is also reduces towards a value which is nothing but VCE saturation. And if you further increase this base current, at that time collector current doesn't increase and collector to emitter voltage is also doesn't reduce. So these two will be looks like constant values, they don't depend on the base current. Now there is no relation between base and collector currents. Okay, so this Out of this one, wherever IC and IB are related at that time, that is going to be treated as active or linear region. Active or linear region. And over here where you are going with, these are saturation point. So even though IB is going to be greater than IB minimum, you can apply more than this current, but collector current doesn't change, collector to emitter voltage also doesn't change. This one is going to be treated as saturation region. Saturation region. So condition for saturation, condition for saturation is nothing but IB should be greater than or equal to IB minimum. IB is nothing but base current supplied. So here actual base current supplied, because of base current supplied we are expecting some current IC. This is IC expected. Okay, and under saturation, whenever you are going in this way, what you will expect is nothing but IC saturation. You will take this as VCE saturation. Whenever the collector to emitter voltage is taken as VCE saturation, by that time whatever the collector current results, that collector current is treated as IC saturation. Okay, and even though you are applying IB greater than IB minimum at that time, okay, you may expect a collector current using that relation. So IC expected, you can write in this way without IB, IC expected. IC expected should be greater than or equal to IC saturation. If we don't know the base current, otherwise if IB is equal to 0, at that time you can use this equation for the condition for saturation. IC expected should be greater than or equal to IC saturation. IC saturation can be calculated by substituting VCE as VCE saturation, and VCE saturation has specific values. Okay, VCE saturation is 0.2 volts for silicon and 0.1 volt for germanium whenever it is NPN transistor. So now we will calculate. Step 1 is nothing but we will calculate IC saturation from this for the given circuit. Step 2 is nothing but we will expect what is the expected collector current for the given input voltage. That we will calculate, we will compare whether this condition satisfies, it will be in the saturation region, otherwise it will be in the active region. Okay, so first we are going with, this is a circuit given and we are going to calculate IC saturation. By that time we are assuming that one there is a VCE saturation is going to be taking place at collector to emitter. So IC saturation, step 1, IC saturation is nothing but 10 minus VCC minus VCE saturation, that is nothing but VCE saturation divided by, okay, 10 kilo ohms plus 1 kilo ohm, which is nothing but 10 minus 0.2 divided by 11, which is nothing but 9.8 by 11. So it will be around, okay, this will be around 9.8 by 11 milliamperes. So we'll go in this way, 9.8 by 11 milliamperes. If you have calcio you can do it, otherwise this is sufficient. The value is going to be lesser than 1 milliampere, what we can think. Second step is nothing but calculate IC expected. IC expected is nothing but because of input voltage you are going to be getting base drive, and that base drive is going to be making some current. That current is nothing but flowing in this direction. Since base current is 0 given, so that we are calculating the IC expected because of input voltage. So IC expected we are going with. For that one, apply KVL across base emitter loop. Base emitter loop is nothing but 2 volts minus VBE saturation minus IC expected into 1 kilo ohm is equal to 0. So base to emitter saturation voltage is standard value, which is 0.8 minus IC expected into 1 kilo ohm. From this one we can write it as IC expected is 2 minus zero point 0.8 is 1.2 divided by 1 kilo ohm, which is 1.2 milliampere. So compare, IC saturation is less than 1 milliampere, that is the transistor largest possible collector current is less than 1 milliampere. But what you are applying the input voltage is nothing but because of that one what you are expecting is IC expected is 1.2 milliampere, but the collector current doesn't go towards this value because it is limited to 9.8 by 11 milliamperes, which is less than 1. So if you compare, that is what we can say is IC expected is greater than IC saturation. So the transistor is already in saturation. Transistor is in saturation region. Transistor is in saturation region because transistor already got saturated whenever it reaches 9.8 by 11 milliamperes, but you are increasing the input voltage such that it may go towards 1.2 milliamperes, which is not possible. So that we can say that when the transistor has already reached the saturation point, it no more depends on the input or input current and input voltage, such that your expected value of 1.2 milliamperes doesn't meet. So the right option for this question is B, saturation region. Thank you.